Hello, folks. It's really wonderful to join you online. My name's Corey Davis. I'm the Digital Preservation Librarian at the University of Victoria Libraries. You can see my email there, and please do feel free to reach out after you've viewed this presentation if you have any questions or you would like to talk about any of the things that I'll be talking about today. I'd be really happy to connect. So I just finished a 6-month research leave at the University of Victoria Libraries where I focused on large language models, something called Retrieval-Augmented Generation, which we will be talking about during this presentation, and a focus on the mechanics behind large language models, behind Retrieval-Augmented Generation, and why there can be problems in this area and how we might try to address those in a research library setting. So to start out with, I'd like to introduce those of you who might not know Bob. This is Bob Belcher, and he is from an animated sitcom called Bob's Burgers. And Bob's Burgers is something that I comfort watch. So whenever I'm working in my office, I'll have that playing in the background. If I'm doing some menial work that needs not so much of my attention. And it's a good area of focus for me in terms of large language models, because if a large language model starts to hallucinate, and we've all heard that term, when it comes to this domain specifically, I'll be able to tell quite quickly because I've seen the episodes, each of them, so many different times. Not necessarily very proud to let you all know that, but it's a really good way to ground truth facts when dealing with large language models. And so when I go to, let's start with ChatGPT here. When I ask a very sort of niche factual question about the show Bob's Burgers on ChatGPT, I ask, what's Teddy's favorite hammer? And Teddy was the character you saw on the second slide there. And very confidently, ChatGPT lets me know that it's Old Hickory. And it even tells me a specific episode and season where, where this is mentioned. And I'll just say right off the bat that this is completely not true, and not only in terms of the name of the hammer, but also the episode as well. Copilot is a little bit more generic, but again, the lucky hammer is it's not correct. DeepSeek, which we've all heard about lately, calls it the one hammer, and again, it mentions another episode different from the episode that ChatGPT mentions, and again, it gets it completely wrong. Claude, which is my favorite hallucination, Francois, which I thought was quite charming. Again, completely wrong. I like at the bottom there, you can see Claude can make mistakes, so please double check responses, which is a good thing to let folks know. And actually, Anthropic, the team behind Claude, does a lot of work on this type of issue. Grok, which is Elon Musk's large language model, again, doesn't make up an answer, but doesn't have the answer. And last but not least, Gemini from Google actually gets the answer right. And one of the reasons why is because it didn't use necessarily its training data. It went out and looked for information on the live web. And that's a version of what we're going to see today, Retrieval-Augmented Generation. So we can see that out of all of those large language models, one of them got it right. So why do these things get things wrong so much? One of the big reasons is, as many of you will understand, large language models are based on statistical patterns. They're not memorizing facts, they're memorizing patterns in their training data. And if some of that, if that data lacks specific information, the model will fill those gaps and it will often get things wrong when it's doing that. So false but plausible details are filled in. And again, with large language models, and this is quite problematic, is there isn't really a way to verify the sources because the way that they're trained, and so there isn't there isn't a ground truth within large language models. So what I explored extensively during my research leave was this idea of retrieval augmented generation that might help reduce these things called hallucinations, where large language models make things up. And what retrieval augmented generation enables us to do is have our own data, our own corpora, our own information uh, transformed into the kind of information that large language models can work with. And we're able to feed that information into those models and retrieve answers using the power of the models to generate natural language responses from that data dynamically. So it augments these models, the generation models, with documents that we can give to it. And it's a little bit complicated how it works here. So you can see up here these reference documents. This is going to be the material that we have at a research library. So it could be, in the case that I'll be talking about today, it could be web archives, it could be a series of PDF documents, any sort of unique digital collection that you have. What happens is you use a very specific type of large language model specific to RAG pipeline to transform those documents into embeddings. And embeddings are high dimensional vectors that basically transform chunks of text into numerical representations, and those representations place that chunk of text in a high dimensional space, in a high dimensional vector space, where semantically similar chunks cluster together. And you store those in a vector database. When you create a query in a RAG pipeline, what happens is that query is again embedded using the exact same model that you embedded your reference documents with. It's given a shape or a place in that high dimensional vector space. And then what happens is you retrieve the top 4, 5, 10 vector embeddings from your reference documents that are closest in that high dimensional vector space to your query. So your reference documents are embedded, your query is embedded. When you go to retrieve, when you go to query your reference documents, that query is itself embedded and matched with relevant text chunks. Those chunks are then combined with the query with any sort of internal system prompts, and these are extremely important because most large language models, in fact, all of them, are very sensitive to um, how your query is actually formed. And then those chunks are transformed back into human readable text and appended to that query. So you have this big package here that includes your user query, any system prompts that tells the system what you want to do, and the text chunks that were retrieved from the vector database after being matched to your user query. So this is a big sort of prompt package that is then sent to a large language model, one that we might understand like ChatGPT or Claude or another one. So that's where this model down here sits, the models we're familiar with. You can also use an open model, something like Llama from Facebook. And then the large language model creates the response. So in trying to understand how a RAG pipeline works and all the different pieces and all the different moving parts, I created a very simple Flask web application using Python on the back end that would take two rather large PDFs that the PDFs are a 2-volume textbook on the Middle Ages. And so I would transform those into vectors and then be able to query those and then use a large language model to get an answer back. Okay, so here is the front end of a short pipeline to the Middle Ages, and you can see here the vector store has already been created. What I would normally do is point to the PDF documents on a local drive. Those would then be embedded and stored, and then I would query. But because that is a very computationally intensive process, it can take 5-10 minutes. I've done that ahead of time. So this is a very simple little application. I'm going to enter a question here. And again, what's going to happen here is we're going to be using our own data to create a prompt package that will then be sent to a large language model for natural language response. So what was the Black Death? Here we go. I'm going to submit the query here. And you can see up here, it's working away. And here's the answer. So what was the Black Death? And what we can actually see here is the the answer, and this is all inferred from our source documents. If we go to the command line, we can actually see here the formatted answer, but also the chunks from the vector store that data was taken from. So it enables us to link back to the original source documents. And go back to the presentation here. So what's happening is we have our source documents here. We're using a specific Python library to extract text from those PDFs. That text is then embedded using a specific large language model transformer for semantic similarity search called text embedding ADA 002. This is from OpenAI, but there are many, many different choices for text embedding models. They can be open via accessed via API or downloaded to your machine. That content is then stored in Face Vector Store. That's a Facebook AI similarity search vector store. Importantly, this doesn't store any metadata. So when we look at our next reg application, we're going to see a different vector store used that can actually link back to the original source documents. When we query, our query is then embedded using the same transformer. And then we retrieve, I think it's 5 chunks in this particular application, but that can be customized. Those chunks are then retrieved. They're matched to the query is matched to the 5 most similar chunks semantically from the vector store. Those chunks are retrieved. Those chunks are added to your query along with system prompts and then sent via API to GPT-4, and we get the answer back. So that's a simple demonstration of a reg pipeline and quite accessible to build, in fact. So the next thing I looked at was something called WARC GPT, and this is a reg pipeline specifically designed to surface information from web archives, which can be very difficult to use otherwise, developed by the good people at the Harvard Library Innovation Lab. And I can't say enough how great it was to have this as a starting point that I could work with. And what WARC GPT does is it uses reg to keep responses grounded in source documents. So those are the web archives that you may have through a tool like Archive It, or even things that you just might get via wget or Conifer or any other source that will create work files for you. And then you can interact with these work files, and that interaction takes place using the inference power of a large language model of your choice. And again, that's customizable. And then the answers from from your query are linked back to original source documents within the WARC files. So unsurprisingly, I crawled the Bob's Burgers wiki, which is a fairly large site, but not too big. I think the WARC files in total were about 10 gigabytes, which is not very large, but because I was just using commodity hardware, MacBook Pro, to do a lot of this testing, it still took a significant amount of time to embed that. So I wanted to find something that was the right size for the hardware that I had. Anything bigger than that would have taken too long. And in fact, even with something this size, a relatively large website, it was very difficult to experiment with different embedding models because the embedding process took up to a week initially for each time. So when you're doing different chunking strategies, when you're trying different embedding models, it's really critical to have high performance hardware because otherwise it's going to take you a really, really long time. Here is the capture from Archive It, and so you can see it was 12 gigabytes of web data, and that's what went into WARC GPT. So I'm not going to demo that right now, just in terms of the time. But what I will say is that I crawled this site. I had everything ready. I got WARC GPT up and running on my machine. I embedded all of the WARC files. I configured the large language model that I wanted to use for inference. And then when I went to start asking it questions, it failed miserably. And this was not the fault of WARC GPT, as we're going to see, because there's different ways that we can tweak things within this piece of software or within something we might build ourselves. But during my research leave, what this basically led to was an exploration of, okay, why am I having these problems and what do I need to do to solve them? So just to quickly overview the configuration I had for WARC GPT initially. Here is our source documents up here, the Bob Burger wiki, Bob's Burgers wiki. Um, Beautiful Soup is used to extract HTML text from the web files, and the same PDF Python library is also used. So this enabled us to grab all the text out of these source documents, embedded with a different um, a different transformer. This is E5, and this is openly available via Hugging Face, which is a model hub. And we stored it in something called ChromaDB, again, another open source tool that has, unlike Face, the vector store used for the previous application, it allows us to keep metadata, so we can keep that connection between the original source of the chunks, the original WARC files, and the original URLs that are associated with that. And very similar to our previous reg application, the query is embedded using the same model. That query is then matched with n number of chunks within the vector store. Those chunks are retrieved. They're augmented with the query plus systems prompts. We're going to look at that in a minute. And then this query was actually sent to an open model, which is Llama 3.2 using the OLLAMA framework, which allows you to run open large language models locally on a machine. And then you can see here that I was getting very poor answers, and this was a consistent thing. So this is where, I was about a month into my research leave, and I was like, okay, I'm going to really dig into this thing. I'm going to figure out what retrieval-augmented generation is, how large language models work, and see if I can solve these problems so that when I come back into the digital collections environment, I can speak with our developers in a meaningful way about what we would actually need to do to get something like this up and running at scale with our collections. So possible solutions were one of the really important parts of a reg pipeline is your data, obviously, garbage in, garbage out. So with Archive It, the works are created for human consumption. And what I mean by that is that people are going to be navigating through an archived website using something like the Wayback Machine. And so it has to grab all of the different files that are used by that website to create the display. So all the JavaScript, all the style sheets, all of the images, any embedded media, all of that stuff is noise to an embedding model that's just focusing on text. So could we actually get cleaner files to start with? And the text extraction using Beautiful Soup, um, could could I tweak that so that it focused just on the tags within the HTML that had the really good content? What happened in WarpGPT with the out of the box configuration of Beautiful Soup is it was just capturing, I believe, a div tag that had all of the content, including a lot of the navigation menus, and that introduced all kinds of noise into the semantic signature of the chunks that were being embedded. And so it was really hard to match a really semantically dense query to a chunk that was full of all this noise. And so could we do a better job at extracting text? And then tweaking the different models. So not only the large language model that's used for inference at the very end. So in this case, Llama from Facebook. We used GPT from OpenAI in the first example, but also the embedding model as well that that creates the chunks that are stored in the vector database. There's different ways to, there's different vector databases to explore. There's different chunking strategies. The chunks that get embedded can be larger or smaller. They can have overlaps to maintain semantic coherence across different chunks. So those embedding strategies are also really critical. And then finally, that the system prompts, the internal prompts that tell the large language model what to do with the data that you're giving it are also something that are absolutely critical. So in order to understand this better, what I wanted to do, instead of tweaking sort of the under the hood um, bits and pieces of WarpGPT, which is very doable. And again, this is not a critique of WarpGPT itself, because a lot of the things that I have done here in this sort of bespoke or homegrown RAG pipeline for web archives could be done much simpler within WarpGPT, but I really wanted to dig into it and build my own pipeline so I could really understand the mechanics of it and what was going on. So what I did is I decided to address some of the issues that I identified after all my research with WarpGPT and build something that could do a much better job. So here's a very simple interface using, again, Flask for the web app running locally on my machine. You can see the top box there is where I enter my query, and then I can tell the system how many different chunks from the Chroma vector store that I want brought back and appended to that query. And then I have my system's prompts here that can be changed depending on the different contexts. So I wanted to be really clear about what I wanted the system to do. And again, this element of prompt engineering is absolutely critical. This is something where I wanted to surface this in the app and provide a space here in this text box to tweak that, so you could see how it impacts a user query. And again, in a RAG pipeline, if you add the system prompts into the user query, as you would normally do in something like when you're working with ChatGPT, those system prompts create they form part of the semantic signature of the query that's then going to be matched with the text chunks in your Chroma database. And again, this will introduce a bunch of noise into the query because you're not wanting to match any of this semantic content. These are just instructions. So in a RAG retrieval system, it's very different than if you're talking directly to a large language model. You need to separate your query, what you want to find, from the instructions that you're giving the system. And so what I found with these tweaks, first and foremost, I used wget and a bunch of parameters within that to exclude anything but textual content, and then tweaking the beautiful soup Python um, parameters to looking at the source code in the HTML and saying, okay, this is the part of the web page that has the content that I'm interested in. And so I was able to reduce the overall size of the work for the wiki from 12 gigs to about 2 or 3 gigs. And then using the same model, the same database, but with a significantly improved system prompt system, so I could tweak and play around with what I wanted the system to do in that text box that we saw right here in the previous slide. And then using via the OpenAI API, the most high performance model that is available at right now, which is GPT-4 from OpenAI. I was able to, by tweaking the cleaning the data, extracting it more effectively, using better system prompts and a higher performance model, I was able to get the right answer. And so this was happening consistently time after time. And you can see all of the different pieces here that are in play when you're trying to build out a reg system and the different things that you need to experiment with. So some of the significant variables in the workflow are source document quality is huge. The embedding model performance is also really critical, but because it took so long to embed even a small website on some commodity hardware, I wasn't able to experiment with that as much because again, it would be a week plus sometimes for the large 12 gig work files. And so having high performance machines to run this stuff on is really critical when you're experimenting. The chunking strategy is also really critical. So um, how do you break up the text within your source documents effectively so that queries can be matched with it? So if your source documents are something like FAQs, you're going to want a smaller chunk versus something like what I did on a wiki, where the context is larger and you're reading paragraphs at a time as opposed to smaller text snippets. The prompt design is absolutely critical, and I can't overstate enough how important prompt engineering is in a reg system, and it's also extremely dependent on specific models. So if you swap out a large language generation model, say from Llama to GPT-4, your prompting strategy is going to also need to change significantly because they're tied together. You're speaking to a specific large language models. There are ways to generalize that I'd like to explore more, but I wasn't able to do that during this research leave. So after all of these things that are in the various different reg workflows, I got really excited about the potential for the application of a reg pipeline to all of the archival information packages that we currently keep that are part of our digital preservation mandate. So we have from all of our different access platforms, be it Dataverse, DSpace, Vault, which is our Fedora-based repository for digitized collections, Archive It, et cetera, et cetera, et cetera. All of this stuff is extracted from those access platforms and stored separately. And this corpus of data is a really promising place to start with working through some of these things. So you can see the connection there between our efforts on the digital preservation side of things and now being able to dig into these large language model explorations using RAG. And again, this is something that I am not a overly technical person. I used ChatGPT Pro and Claude Pro to help me write the Python and create the Flask web apps. And all of the components that go into these they're open tools, and you're able to build an end-to-end reg pipeline that can be encapsulated on local hardware. So if you run a open model using something like Olama, if you use, um, you know, you can download transformer models for the embedding. Everything is stored locally. So you could actually build something and try it out without using any APIs, without schlepping any of your data out to a commercial service provider, which we're really excited about because in our special collections and university archives, we do have a lot of restricted or sensitive records that we would like to try pushing into these reg pipelines to see if we might be able to get some increased productivity out of especially things like description of personal papers, entity recognition, and things like that. So if you're going to do this work, it requires fairly beefy hardware. So you need a lot of, I mean, the key here is the GPU and the virtual RAM that's associated with that, but also the CPU and the system RAM is also really critical, and lots of space to store stuff so that it can be retrieved efficiently. This can be extremely expensive if you're using a service like AWS, and there are also privacy implications when that data is in the cloud. There are also in Canada right now significant geopolitical concerns around using large American tech providers and what that might look like in the future, how those services might be leveraged in a negative way. And so we're looking locally at the University of Victoria to build some of this stuff locally by purchasing hardware. Excuse me. So the next steps for us are we have this on order now, which is a really beefy Dell desktop that has a kind of a rack configuration, so we can plug it into our data center for excellent network connectivity. We were able to afford a single very beefy GPU, lots of CPU, lots of RAM, and lots of SSD storage. We are also working with our research computing services to potentially have them on some of their GPU-enabled hardware run some of the models locally. So our machine would be used for the data cleaning and text extraction and embedding and the vector store. But the really computational, like running the really big open models, could happen on more high performance hardware. So our next project we're wanting to do is look at a much larger corpus of information, which is about 100 years of digitized newspapers from locally from Victoria, and look at how we can use some AI-powered OCR cleanup tools, and then try to embed those in a way that we can have a conversational interface so people can query that corpus in the way that they would use something like ChatGPT. And so that's where we're going in the next year or so, to see if on another larger, more challenging corpus of really rich, valuable information, if we can get this working and all the different bits and pieces to see if we can actually get this going in a production environment. So thanks very much, everyone, for listening today. I really appreciate your time and your attention. If you'd like to dig in, I don't know if you want to, but if you want to read another 100 pages on this stuff, I provided a URL there. You can just do a web Google search for this. This is in our institutional repository, which was indexed by Google Scholar within a matter of days, which is really great. And please take a look at that if you have further interest and reach out otherwise. And I hope you have a great day. I'd like to thank CNI for giving me the opportunity to present to you.